Before a star can shine, it waits, in silence, in cold, and in darkness. It begins not as a sphere or a spark, but as a cloud. A massive drifting collection of gas and dust, sometimes stretching across hundreds of light years. These are stellar nebulae, giant molecular clouds that for the most part appear still and empty. But deep within them, something extraordinary is happening. They don't glow at first. In fact, they often appear as dark blotches against the starry background, not because they're empty, but because they're so thick with dust that light can't pass through. They're filled with hydrogen, the simplest and most abundant element in the universe, along with smaller amounts of helium, carbon, oxygen, nitrogen, and other heavy elements. These are the raw ingredients of stars. But material alone isn't enough. Left untouched, these clouds can float undisturbed for millions of years. What a nebula needs is a trigger. It might come in the form of a nearby supernova, an exploding star that sends out a shockwave, or a gravitational nudge from a passing object. Even the slow rotation of the galaxy can stretch and disturb a nebula just enough to make it unstable. And once that stability is lost, gravity takes over. Inside the cloud, regions begin to collapse under their own weight. These pockets, called dense cores, become the earliest seeds of stars. As gravity pulls more matter inward, these cores grow denser and hotter, setting the stage for something new. This is how every star begins, not with a bang, but with a slow, quiet fall. One of the most iconic examples is the Orion Nebula, located about 1,244 light-years from Earth. It's part of a larger molecular cloud complex and serves as a nearby example of an active star-forming region. When we look into Orion's sword through a telescope, we're not just seeing gas, we're looking directly at a stellar nursery mid-process. There, we've identified hundreds of protostars and disks of material forming around them, called proplyds, which suggest planets are also beginning to take shape. In its core lies the trapezium cluster, a group of young hot stars that light up the entire region. The Orion Nebula is not rare, it's just nearby. Across the galaxy, similar clouds are forming stars at different rates and stages. The Carina Nebula, for instance, is over 7,500 light-years away and forms some of the most massive stars ever discovered, including the highly unstable Eta Carinae. Not all stellar nebulae are active, but some are still very quiet, patiently waiting. A prime example is Barnard 68, a dark molecular cloud about 500 light-years away. It's a small, isolated cloud that looks like a dark circle against a backdrop of stars. Right now, Barnard 68 is stable, but over time, gravity may overtake its internal pressure. When that happens, it too will collapse, and a star will begin to form. In some nebulae, stars have already started to form, and when they do, they make their presence known. Young, massive stars emit huge amounts of ultraviolet radiation, which ionizes the surrounding hydrogen gas and causes it to glow. These are called H2 regions, and they're some of the most visually stunning parts of the galaxy. Take the Eagle Nebula, for instance, home to the famous Pillars of Creation. These towering columns of gas are being eroded by radiation from newly formed stars. Stars that, ironically, are destroying the very cloud that birthed them. Star formation is not peaceful. It's competitive, messy, and full of feedback loops. The heavier elements found in nebulae, carbon, iron, oxygen, weren't formed in these clouds. They came from stars that died long ago, returning their material to the galaxy via supernovae or stellar winds. This means stellar nurseries are made, in part from the ashes of dead stars. The universe doesn't waste anything. It recycles its dead to give birth to the next generation. In every region of a molecular cloud, there's a constant battle between two forces. One is gravity, quietly pulling everything inward. The other is thermal pressure, pushing outward due to the random motion of gas particles. For millions of years, they exist in balance. But when that balance is disturbed by a nearby supernova or by internal shifts in temperature or density, gravity can begin to win. If the collapsing region exceeds a certain size or mass, known as the Jeans length and Jeans mass, the collapse becomes inevitable. It starts slowly, then accelerates. The result is the gradual formation of a tightly packed hot core, a future protostar at the center of the collapsing material. As the collapse progresses, the center grows denser and hotter. The surrounding gas, still falling inward, forms a disk. This accretion disk funnels material into the center and will later become the birthplace of planets, moons, and other celestial debris. The energy from the infalling material isn't lost. It's converted into heat. That's why these objects begin to glow faintly in the infrared. It's not nuclear fusion yet. It's gravitational energy, radiating as heat. These cores don't go down quietly. Many of them begin to spin, forming jets, columns of gas that shoot out from the poles. These bipolar outflows are common signs of early star formation. In the Taurus molecular cloud, about 450 light-years from Earth, astronomers have closely studied a protostar known as L1527. This object is in the middle of its collapse. It's still surrounded by a thick envelope of dust and gas. But thanks to the ALMA, Atacama Large Millimeter Submillimeter Array, we can see the structure forming. It has an accretion disk, it has jets, it has heat rising from within. L1527 is, in every way, a snapshot of a star on its way to being born. Interestingly, one collapsing region doesn't always produce just one star. More than often, as gravity pulls the gas inward, small asymmetries cause the region to fragment. Each fragment can collapse on its own, leading to the formation of binary or multiple star systems. This is how many stars in the galaxy are formed, not alone, but with siblings. T Tauri, a young star in the constellation Taurus, is a famous example of a system mid-collapse. It's actually a binary with complex outflows and variable brightness. T Tauri stars represent a late stage of gravitational collapse, just before full fusion begins. They still show signs of infall, but their cores are nearly hot enough for ignition. Their behavior, irregular, flickering, evolving, offers a close look at what our own sun may have been like during its earliest days. As the core grows hotter, it begins pushing back. The young object emits winds and radiation that push against the infalling gas. These forces help shape the environment around the star and, in many cases, slow down or stop the formation of other nearby stars. This process is called stellar feedback, and it can sculpt entire regions of a nebula. The dramatic shapes we see in images, pillars, arcs, bubbles, are often carved by the intense energy of young stars fighting back against their surroundings. In the Eagle Nebula, about 7,000 light-years from Earth, stand towering columns of gas and dust, known as the Pillars of Creation. These are remnants of dense gas being evaporated by nearby recently formed stars. Inside the tips of these pillars, new stars are still forming, but their time is limited. The very radiation that lights them up is slowly tearing them apart. It's a powerful visual, creation and destruction happening side by side. Sometimes a collapsing core doesn't become a full star. If the object doesn't gather enough mass, less than about 8% of the sun mass, it never gets hot enough for fusion to begin. These objects are called brown dwarfs. They're sometimes referred to as failed stars. Brown dwarfs can still glow faintly in infrared, and they may even have planets orbiting them. But they never truly ignite. The collapse phase lasts a long time, but not forever. For stars like our Sun, gravitational collapse might take 10 million years. For massive stars with stronger gravitational pull, it can happen in just hundreds of thousands of years. Once the core temperature reaches about 10 million Kelvin, hydrogen atoms begin fusing into helium. That moment changes everything. Collapse gives way to light. Gravity yields to fusion. The protostar becomes a star. But how long does this protostar phase last? It depends on the mass of the forming star. For low-mass stars like our Sun, the protostar stage might last a few million years. During this time, the object becomes increasingly warm and compact. For high-mass stars, the process is much faster, sometimes taking only a few 100,000 years. Eventually, as mass builds and contraction continues, the temperature at the core approaches 10 million Kelvin, hot enough for hydrogen nuclei to begin fusing into helium. This moment, when nuclear fusion ignites, is the end of the protostar phase. The star now produces its own energy from within, balancing gravity with outward radiation pressure. It joins the main sequence, and the star is born. This is AstroTheatis, exploring deep space, discoveries, and the limitless possibilities of the cosmos. If you enjoyed this journey into the unknown, then you will like the recommended video above. Stay curious and keep looking up.